As was said, I am Matthew Lauber. I am here to present about Pika, AMQP library for Python. As we can see, I've been off to an excellent start today, but we'll go ahead and keep flowing into things. So to start off with, we need to go over what is AMQP. AMQP stands for Asynchronous Message Queuing Protocol. It is a third-party protocol for storing and passing messages between services that will manage the reliability, the routing, and the deliverability of all of your different messages between services. So you don't have to manage synchronicity, you don't have to worry about order, you don't have to worry about duplication, you don't have to worry about losing messages. It will take care of all of that for you and can even do certain types of filtering and routing for you as well. So kind of just need to go over exactly what AMQP goes into, what the parts of AMQP are, so that you understand as we go through this presentation exactly what I am presenting and what these different parts do and how they interact together. So the first thing that you need to understand about AMQP is where the messages come from. This messages come from what is called a producer. A producer is just any piece of code that you write that creates a message and sends it to an exchange. That goes into the next thing, an exchange. Exchanges are the first part of the AMQP protocol that you will interact with. An exchange is simply a router. It takes a message coming in with a body of the message and a routing key and matches that routing key against any queues that are bound to it and passes it to those to those queues based on the routing key. It puts the body of the message into the queue, and whatever queue it goes into holds the message until a consumer consumes it. So queues are the next part. Queues are where all messages reside. Every time that you want to pull a message off of from one service into another service, it goes onto a queue until that service is ready to accept that message. Queues will hold things generally in first in, first out order. The only time that changes is if you have any reliability issues, if you have a message that is unable to be processed, rather than discarding that message as soon as it is unable to be processed, it can actually be replaced on that queue and will cycle through again, waiting for its turn again. So that's the only time you can get out of order behavior with AMQP. Finally, once you go through queues, you get to consumers. Consumers are the code that you write that accept messages, respond to them, do some type of other behavior, and then acknowledge that the message has been completed. So a couple of things important to note about the AMQP side of things. Now, exchanges are where you filter messages. Every message that goes into an exchange does not have to end up on a queue. It will only end up on a queue if the routing key that is passed in with the message matches the routing key that the queue was bound to the exchange with. They do not hold messages, so at no point will an exchange hold a message in state. Queues are the only place that hold messages. By default, queues will only hold messages in memory unless you configure them to do otherwise. This is for speed purposes, allowing you to handle many, many messages per second. So, can get up to the tens of thousands to hundreds of thousands if you're clustering your AMQP servers and not writing them to disk at all, just storing them in memory. So moving on, we'll go ahead and jump into immediately the first example of what you might want to use AMQP for, workqueues. AMQP workqueues basically allow you to even out a high-rise load-drop service. So if you have something that takes in messages, has tasks that it needs to complete, and it gets swamped with tasks and then has some time to catch up, then swamped with tasks and has time to catch up, you can use AMQP to kind of smooth that rhythm out, give you a responsive front end for accepting messages, and then catch up on whatever backlog you develop during the load times. So the exact way that this flows, and I hope that everybody can see the bottom of the slides there for you, is that a producer sends a message to an exchange. The exchange will stick it onto a queue. In this example, I just named it a queue called hello. And then a consumer pulls the message off of the queue, processes it, acknowledges it, and gets a new message. So a couple of examples of where you might want to use this is a website that accepts orders for processing. The order processing code can honestly take on the order of several seconds to minutes to even just log the stuff and do any of the side processing in terms of credit card validation and everything else that you might need to do. So you'd probably want to stick that on an asynchronous process and not leave your web page spinning there waiting for all this data to be loaded, this information to come back. Another good example is large data analysis. So if you have any type of large data sets that are being passed around. I don't know if you're doing some type of network analysis, network node analysis, or doing anything like that. You can stick these data sets onto the queue. They'll get pulled off by consumers whenever they're available and processed individually. So we'll go ahead and kind of deep dive into the work queue as a first example of exactly what Pika code looks like. So Pika code, we'll go ahead and start off with the first step of the process, submitting code, which basically is a very simple three-line process. So you have to create a connection to your Pika server. Right now I'm using a default localhost, but there are connection parameters that can be passed in there that specify a host and a port and can also support SSL as well. And once we have a connection, that is basically a socket connection between the two of them, we then have to open a channel that will hold the data, will pass the data between the AMQP client, the Pika client, and the AMQP server. This just kind of keeps everything individualized so that if you share a channel or share a connection between multiple services, you can have a channel for each individual thread or each individual process on that. Finally, we have the actual publish command, which is simply called basic publish. For a basic publish command, all you need are three, as a minimum, are three basic parameters. You need to have the exchange. If you use an empty string, it uses the default exchange. You need to have a routing key. Whenever it gets a routing key, it just takes that routing key and matches it against any queues that are assigned to it, to the exchange. And then you have to have the body. This is what goes on the queue to be processed by the consumer. So that's all it takes to submit a job. You can set this up inside of your web server code, inside of any application code. It's very simple, very easy to do. Only has the one dependency on the Pika library. You don't need to have any major setup stuff, any major networking information that you need to manage. It'll take care of all of that for you. Going on, then we go to the other end of things, to retrieving jobs. This is the Pika code that will go ahead. This is the Pika code that will go ahead and do this for you. And all it really does is just takes and creates a event loop that sits there polling for messages that come in and responds to those messages. So we set up, again, by creating a connection. Off of that connection, we create a channel. Now we start getting a little bit different because we need to have a queue that will hold the messages for us. So we go ahead and call the queue declare message with giving it the queue as the name of the queue that we wish to declare. So in this case, we're just using the word hello because it's nice and simple, and that's as close as I could get to a hello world example in Pika. So once we go ahead and set up the queue, we need to create a callback. This is where all the fancy event processing will happen. You create a callback matching this exact format with a channel object, a method object, some properties, and a body, and it will receive calls with messages passed to it, can do any type of behavior that it needs to do, and then when it finishes, it will just be done with that and be ready to accept a new message. Once we have set that up, we have a callback ready to handle messages. We need to tell it that we're going to use that callback to handle messages from this queue. That is where the basic consume command comes in. So this is channel.basicConsume. We pass in the callback method, passing around a function, yay for first-class functions. And then we pass in the queue name. So in this case, we're using the word hello. So it tells it, bind this callback to the queue hello, and then we tell it channel.startConsuming. This is just basically a while true loop that will sit there polling, waiting for messages to come onto the queue, take a message whenever it's available, call the callback, run any processing that's done in the callback, come back to this event loop and look for a new message. It's a very simple looping process that just takes care of all the behind-the-scenes stuff for you. And I use the term looping process. It doesn't actually run a while loop in the background. It's got some event notification stuff so that you don't have to, it's not consuming 100% RAM or 100% CPU process at that time. So right now, we've got this set up with functions that will just handle the message, and as soon as it's done, it just ends. In more complex examples, we'll implement some error handling and message acknowledgement using some of the method and property pieces of this code. So if you look at this thing, the method and property here we don't use, but we will in future examples to do any type of error handling. That's what that's really there for. Moving on then, we'll go ahead and take a look at queue persistence. So sometimes you want to create queues that last through reboot. You've got a queue that's going, or a consumer that's looking for a queue and is trying to connect. And if the AMQP server goes down, you need that queue to continue to exist so that when the AMQP server comes back up, you can connect again. So this is where queue persistence comes in. This one, again, is a very simple properties that's just passed into AMQP. Good examples of when you might need to use this is if you need messages to survive reboot, if you're not allowed to lose any messages. For example, when we were talking about order processing, can't lose any messages. You don't want to have unhappy customers, so you have to make sure those messages persist. We'll get into that a little bit more because in addition to queue persistence, you also have to tell messages to persist as well. That way, some messages that may be not that important, for example, logs, you can go ahead and if everything goes down, you're not cluttering up your file system, you're not slowing down your entire system, trying to keep all of your logs written to disk instead of just sending them through memory, first in, first out kind of thing. So you should always, it's important to note here that you should always declare the queue before you try to use it, just in case it may not exist at the time the AMQP server reboots, you didn't declare your queue durable, all of a sudden the queue doesn't exist anymore and you can't consume any messages. You declare the queue durable, but something happens, it gets corrupted, you need to recreate that queue. One important thing to note, however, is that because every time you declare a queue, it passes in all the properties. If you try and declare a queue in two different locations, for example, you have two different consumers, and they declare the queue with different properties. One declares it durable, one declares it not durable, one declares it clustered, one declares it not clustered. Whoever declares it for the second time in a different configuration will receive an error telling it that it is not being declared in the correct format. That's just an important thing to talk about right there because that's something that can come back and bite you in the behind it at times if it ever becomes an issue or something. Moving on, we'll go ahead and take a look at the next step into work queues. So we talked about having a work queue with one producer and one consumer. This is good if you've just got some high times and some low times and some ebb and some flow here. But sometimes you just have more stuff coming in than any consumer can process. You just get all of a sudden your service becomes the next eBay, and you've got 100,000 orders coming in every minute, and you need to stay on top of these things, and you just a single process isn't doing it. AMQP takes care of all the behind-the-scenes stuff for you. All you need to do is spin up another one of your consumers, and it'll start splitting tasks off. It basically runs things round-robin style, but what it really does is first available consumer will tell the AMQP server, I am ready for the next message, and the next message will be sent over to them. So it'll manage the queues for you, it'll manage whether or not messages need to be requeued for you, it'll manage whether messages have been acknowledged, if there have been any errors. It goes ahead and just keeps taking care of all that stuff for you. Sending messages to all, in this case, as I said, each consumer gets the message, or a message is only sent to one consumer. Only one consumer receives a message, so if you have multiple consumers that all need to receive a message, you have to do that via a publish subscribe, which will be the next example that we'll be going through. That is configured a little bit differently, but we'll go ahead and kind of just take a look at exactly what goes into this kind of thing. So one of the features that kind of becomes important when you have multiple consumers is confirming that jobs are complete. If a message comes in and it's in an error state, you receive invalid data, I don't know, somebody gives you a 20-digit credit card number. You need to come back and say, this message is a problem, cannot be handled, we need to figure out how to handle this. One of the things that you can do is do basic acknowledgement and basic acknowledgement, not acknowledged. This is just a simple thing that you have to do when you set up your basic consume command. You tell it the no ACK equals false. This tells it that the message will be acknowledged. It will not be automatically ignored as soon as it finishes the callback. And what you have to do is do things with the message, and then if the message has been successfully validated, you call a basic acknowledge, passing in a delivery tag that has been passed to you using that method parameter that I was talking about earlier. This tells the server exactly what message it is being acknowledged, and the same way for basic unacknowledge or disacknowledge. Simple enough right there. Moving on, we kind of go ahead and take a look at error handling. So one way, there's a couple of different kinds of errors that you can have. The first is you have a consumer's running, all of a sudden exception or an error happens or something, maybe the server crashes. Your connection has died, your client has disconnected. AMQP is intelligent enough to say, all the messages that were sent to that client, which have not been acknowledged as being completed yet, we will assume, since the connection has died, that they are in the unacknowledged state and return them back to the message, or back to the queue, and queue them up for the next available consumer. So this way, if you have anything wrong with your infrastructure, anything happens, AWS goes down, all your messages will still stay on that queue for you, and you'll have them there as soon as you can get a consumer up or until the next available consumer. The other thing to think about is if a message comes in that can be handled, but the only way to handle it is to say the data is invalid, we need to deal with it separately. We need to do either a human intervention or we need to look into it because somebody's trying to probe our system and is causing all types of errors, seeing if they can inject SQL or something. A good pattern for this is to set up a special error hospital or an error queue. And as part of the message, you can basically say, take this message that we are given and do a basic publish to error queue with the same body, with the same routing key so that you know exactly where it came from. And then you can do a basic unacknowledge with no requeue. Tells it, don't put it back on the queue. We've dealt with this thing, but we don't want to log it as being handled correctly. So now we'll go ahead and pop into the publish subscribe service. So publish and subscribe is a well-known pattern. It's a way for one service to notify a variety of other services that some new event has happened that they may want to respond to. The way that AMQP handles this and the way that Pika handles this is to the fact that you can bind multiple queues to a single exchange and multiple queues to the same, in fact, routing key. So I was using the routing key hello before, and it was routing to a specific queue. We'll call that one QA. I can use the same routing key again, hello, and route to QB, and that message will be duplicated and placed both on QA and QB at the same time, and the consumers that are attached to both QA and QB will each get a copy of that message. So this can be very useful for computing search engine indices. Many times you want to compute multiple types of search engine indices. You want to have related words. You want to have words in context. You want to have individual words. You can fan this all out to all these different things, compute all these different indices at the same time, and each of these things can run independently, keeping up as fast as they can, and eventually everything will get done. And it lets you also kind of tie your workers to the heaviest load. So if you computing an individual indice doesn't take long, but computing the multiple word one takes a long time, you can have one consumer for individual words and 3 consumers for the multiple words. And it'll allow you to process that simply. Another good example is sending messages to logs. You want to have multiple different logging things. You can do it that way. So we talked about attaching a queue to an exchange before. We basically did the queue declare and the queue bind kind of stuff, but going into deeper detail with that, we have the ability to create individual exchanges that can handle things and can route things independently. So we create a connection and a channel as we did before, and then we can declare an exchange. An exchange, as we talked about, is just something that filters messages, routes messages to different queues. And there are 3 different types of queues here. So I talked about exchange type fanout. There's 2 other types, fanout, direct, and topic. And we'll go into each of those individually as we go. Then we declare a queue, name it task or whatever we want to name it. And then we can bind the queue to the exchange. We just set that up right there. And one of the things that you can pass in with queue bind is, in fact, the routing key that you want to be associated with that. So only messages that match that routing key will be sent to that queue. So going forward, we'll go ahead and take a look at some of the differences in how you can bind queues to exchanges. There are both shared and exclusive queues. So one of the things that you can do with that is basically have a queue that only exists for the duration that the consumer is available. So we're talking about one of the projects that I worked on at one point was setting up a variety of different antivirus tools to run. And sometimes some of those antivirus tools were available and sometimes they weren't. And we wanted to use as many as were available at the time that the file was submitted. So we go ahead, set up all these different queues as individuals, and each time that whenever a client disconnected, that queue disappeared, and we would no longer attempt to send any messages to it since we couldn't run it any longer. So that's an example of when you might want to use exclusive queues. So kind of going into exactly how you do that, it's just another property that you pass in on the queue declare command. You can see in that third line there, I'm actually not passing in a name for the queue. When I declare an exclusive queue, I can allow it to give me a randomly generated name. It'll guarantee that that name does not exist anywhere else on the server for you. That way you don't have any concerns about collision or anything like that between consumers. You can even do an empty queue declare, which will do basically the same thing. It makes sure that nothing exists, but you can pass around the method or the queue name once you retrieve it and bind other consumers to that queue if you so chose. One thing to note here is if you create an exclusive queue, whenever that client disconnects, any messages that still existed in that queue are lost. So you shouldn't use this thing for anything that you need to ensure all messages have been processed, that you have an empty queue before you disconnect or before you delete it. It just isn't a good use case for that kind of thing. And we're going next into queue and message persistence. So I talked about declaring queues durable so that they would survive reboot. What declaring queues durable makes the queue survive, but it doesn't actually tell the messages that they should remain on disk through reboot as well. So this is where passing in delivery mode as part of the basic publish is important. So delivery mode has two options. They have delivery mode 1, delivery mode 2. One is default, says don't store this on disk, don't cache this, just stick it in RAM, put it on the queue, wait for somebody to grab it, remove it from RAM. Delivery mode 2 says cache these things to disk. It is a best effort method. It actually still has a window, small window, when it is coming from the exchange, but before it has been written to disk from the queue. Furthermore, writing to disk doesn't call a flush cache command after every single write, so it may be written only to cache and doesn't always make it all the way to disk if you have uptime issues on your server. Just something to be aware of when you're doing this. And delivery mode is the specific property you use for that. So going forward, we're going to go ahead and start talking about how we're routing messages. So routing messages basically talks about three different types. I talked about three different types of exchanges: topic, direct, and fan out. These have three different sets of properties and how they can filter messages, and they have three different speeds. So depending on your use case, if you have hundreds of thousands of messages per minute, you may find that trying to use a direct exchange is inefficient. You end up having to build up a lot of hardware just because every time that it's running a filter against this against the message, it has to do a complex matching pattern. A direct exchange is kind of a middle of the road thing. It says if the key matches, then we need to send it across, and a fan out exchange sends it to everybody. So one of the important things kind of here is to note that these all have to do with how the routing key that is included with the message is matched to the routing key that the queue is bound with. Going forward, we'll start with the simplest, fan-out exchanges. Fan-out exchanges just allow you to send a task to multiple queues for each message. Doesn't give you any type of filtering, just gives you routing. It's the fastest of them. It can handle hundreds of thousands of messages on a single server as long as you've got consumers who can keep up. Basically, we'll just send them in, send them to queues, let the queues fill up, and keep piling in messages. Doesn't do any type of filtering at all. The routing key doesn't really impact it at all. It's the fastest type of exchange and the simplest. Moving forward, we take a look at the direct exchanges. Direct exchanges are your basic filtering tool. These are how you say, okay, I want messages to go to location A, but not location B. They take a routing key when the queue is bound to them. Anytime a message is passed in that has a published routing key that matches these things, matches one of these filters, it will go to that queue. You can bind multiple queues to a single routing key. So we talked about having a routing key of hello, and we can bind one message to the hello routing key on the queues, the queue key, and then every time we publish a message with the published key hello, it'll go onto that queue. you can bind 100 queues with the queue key hello and publish it, and every time it'll end up with 100 duplicate copies of that message on that queue. This is a basic one that can get you a little bit of speed and a little bit of control. Finally, we'll go on to the topic exchanges. Topic exchanges are the most advanced. They give you wildcard capabilities for filtering. So topic exchanges work basically by defining your routing key into segments. Each segment is separated by a period. You can match exactly on segments, you can wildcard segments, and you can wildcard against multiple segments. So you can say, for example, you want everything that comes in that's logs dot hash sign will get logs dot application, logs dot application dot data, logs dot data, matches against every single combination that starts with the segment logs. On the other hand, star only accepts one, so you can do logs.star.data. We'll get logs.application.data, logs.database.data, but won't get logs.database or logs.database.queries. It gives you a lot of control, takes the server a lot of resources, well, relatively compared to fan-out exchanges, to match, does this type of pattern matching, but it gives you a lot of capability in this kind of situation. Once again, it's the publish key matched against the routing key. So the routing key, or the bind key, is exactly where you need to put in all these wildcards. The publish key doesn't use wildcards in any way, shape, or form. That actually kind of wraps up my presentation. I've got some time for questions right now, and then I've got a working example of using a web server or using Pika with a web service in order to show how this can speed up your web service. So I got a question in the back.
I'm interested to know because we have MQ in our shop. I think MQ follows Advanced Message Queuing standard. Is there an interface for without JMS or JMS the way you do it? Or is there a way you can advance this with that? Is there some sort of like back end or bridge, like a bridge driver?
AMQP is a protocol, not actually a specific server. Pika is specifically designed with RabbitMQ, which is an open source AMQP interface, in mind. However, it does have support for other servers as well. So I don't know specifically whether or not it supports MQ, but as long as it matches the AMQP standard, I would give it a good probability. I'm sorry for failing to repeat the question there. Okay, so the question was, for ActiveMQ, does this library support that type of protocol, correct?
Yeah, not ActiveMQ, that's Microsoft.
Okay.
IBM WebSphere MQ.
WebSphere MQ.
Formerly MQ series, now it's called MQ. Specifically for it. And that's easy to find.
Yes. So the answer is typically it should be able to as long as they match the AMQP spec protocol. Any other questions? Yes.
Do you have any background with Celery? Can you compare and contrast Pika with Celery at all?
Okay, I don't have any specific experience with Celery. However, I'm sorry, repeating the question. The question is, do I have any experience with Celery, and can I compare and contrast Celery with Pika at all? I don't have any specific experience with Celery, although I know that it actually uses basically the same protocol and the same behaviors behind the scenes in at least one configuration. Celery, as I understand it, gives you the ability to do annotations and to basically make function calls, be able to be asynchronous, and be able to be distributed across multiple consumer or multiple worker threads. My specific knowledge with that is that it gives you a very strong, very simple programming protocol for doing things that are request response, send out a request, get a reply back, and then process it. I think that is a very good tool for that type of work where you need to pool tasks among a set of workers. But if you need to do advanced routing, if you need to do something where you're going to send a message to one worker who's going to make a behavioral decision and send it out to multiple workers, I would say that Pika gives you a little bit more flexibility in terms of how messages are routed between things. Other questions? Alrighty, if that's the case, I'll go ahead and flip over and start talking through some of the example code that I've got here. So what I've essentially have created is a very simple Django application that accepts a file upload, does some mysterious file processing on this, and then returns the result of this to the server. It just tells them what the behavior has been here, what we saw from this thing. So we'll go ahead and start off with a simple example here. We're passing in this is Django code, but it's pretty simple. So what we're essentially doing is we're calling the without Pika request. This is a typical synchronous process that's being run on the server. We accept a form that's got a file associated with it. We get the file, and we call a process request with the file and the name. We're doing some mysterious thing in there that really is just being time.sleep3. So we're sleeping for 3 seconds, waiting for this mysterious process to happen. And then we come back to our without Pika function and return our HTTP response. Simple enough example, just shows you what happens when you have a long-running process that happens on a synchronous process for your server. So flipping over to this, I'm going to go into the without Pika, just upload an example text file, give it some random name, test, submit it, and it takes it a few seconds before the page can actually respond and say, document test was indexed. Not bad, but sitting there waiting for 3 seconds for the page to for the file to upload and get processed every single time is going to get frustrating for the user experience. So we can try and improve on that. Pop back over to our code. We can take a look at what we're going to try and do next. We're going to try and separate this out with Pika. Go ahead and accept the file, send off a request to process the request, but instead of actually doing the processing right there on that thread, we're going to go ahead and stick it onto a AMQP queue, waiting for a worker to come around and get it. So all we do is we accept a file via request.files, call process request with the Pika this time, and we go into this function. All this does is we create a blocking connection to our Pika server, create a channel as we would expect. I find that JSON is an excellent format for how you want to pass your messages around. It's a good way of storing complex data structures. This is just my personal preference. You can use XML. You can use base64 encode for all I care. All it expects is a text string. So we put that in there. We're setting it up that way so that we can keep some metadata around it, including like the name of the thing. And then we're publishing it out onto the Exchange with the routing key documents. Come back from this function and immediately return an HTTP response. So flipping back over to my example, we'll go ahead, choose a file, same file, whatever, give it the same name, and submit immediately. And comes back immediately, no waiting for the server to respond, no long-running processing being done in the background, immediate response. Improves the user interface, improves user experience, helps to keep the server up and running quickly, and allows that server to process more requests faster. Because every time that you have to hold a thread open, that's one more thread that your Apache server or whatever server you're using has to have running in order to handle the same number of requests. The less time you spend on each of those worker threads in Apache, the more requests you can respond to per minute. So we put that message onto the queue, but we need to actually handle it. We send it to the Exchange. It's going to go onto a queue. We need to tell it that the queue exists, bind the queue to the Exchange, and handle it in a worker thread that will happen separately. So that is where our Webserver Workers come in. You can set up a nice little pool of these things running in a process, set them up as a separate service that gets started up via initd or however you want to manage that kind of stuff. Doesn't even have to be on the same web server. It can be on a different web server. All it needs to have is a pointer to the same AMQP server that your web server is talking to. A good way to set things up is usually to have one centralized cluster of AMQP servers. RabbitMQ makes clustering very simple, handles all the message synchronicity between the different servers very easily for you. is really just a good solution for that. And then you can have your workers across multiple machines, across multiple operating systems. You can put them wherever you really need to put them in order to make the best use of your infrastructure. Anyway, within our Webserver Worker, all we really need is these basically 10 lines of code. We need to have some way of handling the request, which basically just takes and does some magical thing with it, which is our time.sleep, and then logs that we handled it somewhere. And it has to match that same function pattern. So we have to have a channel object, a method, a properties, and a body, just so that we can have those things all there ready for us. Then we go ahead and create a connection to our Pika or our RabbitMQ server or whatever AMQP server you're using, and declare our queues. We declare the queue documents. We bind that queue to the server. Usually that's already been done for us. Right now we're just going ahead and saying, make sure this queue still exists for us. And then we start our basic consume. We say, call every time that you can get a message from the queue documents, call handle with that message. Start consuming. All it does is go ahead and runs this kind of stuff. We go ahead and pull up our server here. And I've got a worker thread running right here. Every time we send in a message to it, we'll go ahead and see that it handled whatever document we chose. So we'll go ahead and pass in response. Let's sure. Submit. Comes back immediately, tells us response was accepted. We flip over here. We can see it started handling document response and then finally handled document response. So that's how a simple example of how to separate your workers and your work heavy load from your web servers, and you can even separate these things out across multiple machines across your infrastructure. I guess that kind of wraps up my presentation in terms of everything. I was going to say if there's any further questions at this time, please go ahead.
How are you doing notifications back to your front end when your async process stops? AJAX or sockets?
So the question was, how do you respond back to or reply back to your front end that the message has been processed? How do you tell the server that it's ready to be handled? You can either set things up so that it doesn't need a response. For example, in this type of situation, this was, for example, for doing search engine indices. We're not responding to the server at all. Otherwise, you can use AJAX, as you say, or anything like that. One of the typical ways to do it is to set up a reply queue that will accept messages back and have that reply queue be watched by the same one thread wherever you're doing getting the requests and responding to them there. Working with this in a web service example is a little bit more complex just because you've got multiple clients and it's difficult to manage that type of thing, but you can usually end up making an AJAX request that sends out a request for processing and then sets up a thread in the background of your JavaScript that will pull a response page waiting for the confirmation message to come in that way. That is a good way of handling that. If you have more experience with WebSockets or long polling, which unfortunately, just my experience, I haven't had to run into, I've heard about these technologies. I would say they are a good example of a place to implement that, because they can keep that connection open, listening for data without having to make multiple requests against your web server. Other questions? Well, then I thank you, and if you have any questions that you want to talk to me about later, I'll be around. Thank you.